Alright, hi y'all. Today we're going to be going over straight line approximations, going from straight line approximations to op-amp configurations. Now, before we get into this specific problem, we need to understand what these op-amps give to us in straight line approximation sketches. So let's look at these and let's figure out the sketches here. We're going to be labeling these arbitrarily, 1, 2, 3, and 4. We will not be dealing with this one or this one because they have no poles and zeros. They have no j omegas to, for us to consider any poles and zeros. So we'll skip those. They don't matter to us, essentially what I'm saying. So how do we get these weird sketches that, Dr. Livanov has been giving us? And yes, he's gone through these, but they aren't, he explained them actually really well, but obviously it doesn't matter how well he's going to be going. Everyone forgets stuff, So I'm just going to be going over this very, very briefly. If you want a more in-depth, go to Dr. Livanov's classes and he'll, not his classes, but his recordings, he'll tell you all stuff. But for this, what we're going to be looking at is we're going to be looking at this transfer function for number 1. What do we know about the transfer function for number 1? Well, we know this is a pole. We have one pole here. What else do we know? Well, we know this is not a 0, but it's actually our a of j omega value. What does a of j omega tell us? Well, a lot of the times it tells us the slope before our first breakpoint frequency. It can also tell us where we start. But more importantly, of course, we want to know where the slope is before our first breakpoint frequency. We know there's one pole, and we know there is an omega here. It's right there. So we know there's an omega in the numerator that is not part of a 0. That tells us we have a slope of 20 decibels per decade before the pole. And now when we hit the pole, we end up flattening. So this is what we call a high-pass filter. Now let's go to number 3. Same thing. Let's look here. We have a pole here. Okay. And for this one, our a of j omega isn't, it doesn't have an omega. So we know there's a breakpoint frequency considered as a pole, and before it, we have a slope of 0. And it hits the pole and it goes down 20 decibels per decade. This is a low-pass filter. Now let's go to number 2 and 4. Number 4, we notice here we have a pole and we have a 0. This might be a little more difficult because we have both. How do we know what comes first? Well, this is when we have to check its end behaviors. So we have to check when omega approaches 0 and omega approaches infinity. How do our transfer functions change? Okay, so how does our transfer function change when omega approaches 0? Well, let's first look at our op-amp schematic. When omega approaches 0, C1 will become what? An open circuit. So what do we know then? Well, when our C1 becomes an open circuit, we know that it will be approaching 0. Our magnitude will be approaching 0, or our gain will just be 1. So our 1 plus R2 over R1 will be 1, or R2 over R1 is equal to 0. Now, what happens when omega approaches infinity? Well, then the capacitor will become a short circuit. What happens to the capacitor becomes a short circuit, and it resembles this up here. You can replace this capacitor with ground, and it's the exact same circuit as the one above. So what happens? Then we have a gain, h of omega, is equal to 1 plus R2 over R1. Or magnitude in decibels is equal to 20 log of 1 plus R2 over R1. So what does that tell us? Well, that tells us the graph will always be greater whenever omega approaches infinity. So we have a starting at 0. So we'll say this is 0, it's starting. It hits our 0 here. Well, we don't know that yet. But then we know this pole, and this becomes 1 plus R2 over R1, 20 log of it. And we know it ends up going at the end. It's greater than 0. It would always be greater than 0 because R2 over R1 can never be negative. So how can it go from 0 to 20 log of 1 plus R2 over R1? Well, it has to increase. So then we know our 0 is here and our pole is here. If you want to go through 4, it's the exact same process. We assume omega goes to 0, and we notice this becomes an open circuit. C2 becomes an open circuit. And we're left with, again, this non-inverting input or amplifier. So then what we have is, when omega approaches 0, we have this high value. Then when omega approaches infinity, it shorts R2, which creates 1 plus 0 over R1, which becomes 1, or 20 log of 1 is 0. And again, we have to go from top to bottom some way, and that's how we do it. So we consider this a step down, and we could consider this one up here a step up. So 2 is a step up, 4 is a step down. 1 is a high pass, 3 is a low pass. If you really want to go through it again, go through Dr. Litvinov's, I believe it's, I can't really check right now, but he goes through how he, deliberately checks the in behaviors of your circuits, and he can go through it pretty well. But for this problem here, what we have to notice is we're going to be using superposition to create this black output figure. Okay, so what we're going to do first is we're going to create 2 of our own inputs to create this output. The way you do this is you create 2 graphs that you know are true based off our sketches. You cannot make up your own. You only use the sketches here that we've created to sort of, add up to create this final black output. So that one goes there, and then the other one goes here. But why does it go there? Why not have red go just like I had, and then blue go here? That feels like it makes sense. Well, remember, when we do superposition, and let's say we have red as input 1, plus blue as input 2, so we'll label this 1 and we'll label this 2, and black is the output, and I'll say this is, green is output here. When we add up the decibels at each of those frequencies, they should be equal to that black output decibels. So let's check. Let's check at 100K. Let's check here and here. What is red? Well, red is 20 decibels. Plus, of course, superposition, we always add. And then this one is at negative 20. The black line should be lying at 0 decibels for 100K. And we notice it is. That works out. Let's check another point. Let's check, I don't know, here and here. What do those tell us? Well, we notice that red is at 20 decibels, and we add, what is blue at? Blue's at 0. The black line should be at 20 decibels, and it is. So this works perfect. Now, we have to figure out, we have to match the drawings we made to the schematic we want. So what does input 1? Well, our schematic shows it's a high pass. So we use 1 plus, what is input 2? Input 2 is the low pass, has 1 pole. So we do 1 plus 3. So let's draw these out. Okay, so we have R2, R1, and C1. And then we do plus, what is 3? 3 looks like this. Okay, so we have V in here. And we notice both of these are inverting inputs. These are both inverting amplifiers. Okay, so, and we'll label this R3, C4, and R4. And this is our VO. Okay, so we want to add these. What else do we do now? We know the two different amplifiers, and we have these kinds of straight line approximations drawn. Okay, first thing we should do, we should look at the end behaviors for both of our schematics, or both of our straight line approximations, to calculate the values of the resistors. What do I mean by that? What I mean by that is, let's look at input 1. What does the graph tell us? Well, the graph tells us as omega approaches infinity, the value of our magnitude should be 20 decibels. And that has to be true, right? Looking at this, as omega approaches infinity, our value is 20. It won't change. It's going to be the value. Okay, well, what is h omega of our first input as omega approaches infinity? Remember, when omega approaches infinity, the capacitor shorts, and what we're left with is an inverting amplifier with R1 and R2. So we have h of omega is equal to negative R2 over R1. Now remember what we did before. These are not the same. This is in volts per volt, and this is in decibels. So what do we do then? Well, we know 20 log of h of omega is equal to 20. H of omega, for this to be true, h of omega must be 1. Or 10, sorry, 10. Right? Yeah, 10. I make sure. So that means our negative, or really this should be absolute value, sorry. This should be absolute value. So that means R2 over R1 has to be equal to 10. So we can say R2 is equal to 10 R1, meaning R2 is equal to, we'll make R2, or we'll make R1 equal to 10K, and R2 is equal to 100K. So we found our resistor values. Perfect. I'll show y'all steps to do this after this problem. It'll make these questions so easy, like for real. If you want to skip to the end, you probably can. I'll go through them. So R1 and R2 we know. Now, how do we find this value C1? How do we find the capacitor value? Well, what we do for that one is we look at the poles, or the zeros, the corner frequencies more likely. So for input 1, where's our corner frequency? Remember, look at the red color on the Bode plot. There's a pole at 10. That's pole 1. This is pole 2. So pole 1 must be equal to what? Well, let's look at the transfer function for our first amplifier. Here, pole, that's the denominator. But pole 1 is actually going to be 1 plus j omega divided by what? 1 over R1 C1. our pole is 1 over R1C1. If you want to know how I did this, I'll show you all real quick. 1 plus j omega over pole is our basic form. We know that 1 plus j omega R1C1 is equal to 1 plus j omega divided by 1 over R1C1. And we know pole here is underneath j omega. So is 1 over R1C1. That's how I got the pole. So, now that we have that out of the way, what do we know? Let me move this out of the way so I don't accidentally press it. Well, we know R1, and we know pole 1. That means C1 is equal to 1 over pole 1 times R1. Just rearranging, doing some algebra there. Pole 1 was 10. So this is equal to 1 over 10 times R1. R1 we let to be 10K. So C1 is equal to 1 over 10 times 10. What is that? 1 over 10 times 10,000, by the way. 10K is 10,000. That's going to be 1 times 10 to the negative 5th farads, or 10 microfarads, it should be. So we found R1, C1, and R2. Now we do the exact same thing for the second input. If you want to do this, do it for me, please. It'll help y'all understand this a lot. So the first step to doing this is looking at the in behavior of our second Bode plot. Our second input, we notice that as omega approaches 0, we choose omega approaching 0 because it becomes a steady value. We do not want to choose omega approaching infinity because it changes values over time. So, omega approaching 0, we know the capacitor opens. Well, before we do that, let's figure out what h of omega is. Well, whenever omega approaches 0, we have a decibel value of 0. Now, analyzing our circuit, C4 becomes an open circuit. That means we're left with, again, a very simple inverting amplifier. So then what we know is, we know h of omega for this graph is negative R4 over R3. Now, in decibels, this is equal to 20 log of R4 over R3. Remember, doing the absolute value. And this must be equal to 0. What must R4 over R3 be for this 20 log to be 0? It must be 1. So R4 over R3 has to be equal to 1. So we can choose, R4 equal to R3. Let's just pick 10k ohms because we picked 10k ohms for the 1 over there. So we know what R4 and R3 is by choice. Now, how do we choose our capacitor? How do we solve for the capacitor value? We do the same thing. We look at the pole or the 0 respectively, however you want to do it. We look at our pole here. Pole 2, that corresponds to our second input. And what I mean by corresponds is, do you notice how in the first input, in that red Bode plot, we have a break point frequency at P1 for the red. It doesn't happen at P2. But for input 2, it happens at P2. It does not happen at P1. So that's how we choose. We don't just choose willy-nilly, we choose which one affects it. So P2, we know P2 is equal to, well, what is it equal to? It might change. Well, let's look at the transfer function here for number 3, right? Yeah, 3. So for 3, it's the same thing as 1. Wow. 1 plus j omega R2C2. So we know then that P2 must be equal to R1 over R4C4. Again, we're doing the same algebra that I showed y'all earlier for P1. C4 is equal to 1 over R4 times P2 is equal to 1 over 10k times, what is pole 2? Pole 2 is 10k, perfect, wow. So C4 must be equal to 1 over 10,000 squared. That's equal to 1 times 10 to the negative 8 farads, or 10 nanofarads. And we're done. Not necessarily, but we're essentially done. We figured out the values. That's all we really need. We just need to put this together, right? So what does it say? It says design the circuit so that it is not sensitive to changes in the source resistance. Not sensitive to the changes of source resistance. What does that mean? Okay, so that means if we change the resistance of our source, our output voltage will not change. Okay, well, let's look. Let's analyze the first circuit. If we change the resistance value of Vn, will it change the output voltage? Okay, well, let's look at our gain, negative R2 over R1. Of course, if we change R1 value, because, they'll be in series, we'll add them together. Will it be sensitive? Okay, well, I beg to say it might. It will. So our gain will be decreased by a little bit, however much. Design the circuit so that it is not sensitive. Okay, so we would have to choose large enough values, essentially. If we choose large enough values for R1 and R2, what we can do is we can make the source resistance, 50 ohms, 100 ohms, however much, negligible. So we could pick 10k ohms. That's perfect. That's perfectly fine. It'll become negligible. So it does not matter which input we use. So let's put 1 plus 3. Let's do this here. Okay, so we have this here, minus plus, and we just put these together. We don't have to worry too much about it. And this is ground, and now we put in 3. Okay, and we draw this. Okay. And VO is there. Perfect, and VN is here. Okay, now let's label our values. C1 is 10 microfarads. R1 was 10k ohm, right? 10k. R2 was 100k. Now we chose R3 and R4 are both 10k. And C4 was 10 nanofarads. There we go, we're done. That's our answer here. Of course, there are multiple answers to this because you can choose R2 and R1 to be anything you want. They just have to have the resistance or the division, if you put 100 over 10, to be 10. So that would be our answer here. Be careful about what they say at the end whenever they say design the circuit so that it is not sensitive to the changes in source resistance. They could also say design the circuit so that it is not sensitive to the so that the input resistance does not vary with frequency, just like this next one that we're doing. Hopefully y'all can see what all of this was. I'm going to copy this because I don't want to have to do that again here. All right, so let's look at this now. Let's look at this one. Let's do this one a little quicker. I don't want to have this video be super long. So first thing here, first thing I like to do is notice our poles and zeros. Let's label them a little different. So we know there's a 0 here because it goes up by 20 decibels. And then we have a pole here because it comes back down. And then we have another pole here at P2. Okay, cool. Now let's create 2 inputs such that the addition of them becomes this new black output line. So what do we have here? We have, well, this first looks like it goes up and then it flattens out. That's a step up. Okay, well, let's draw this step up. I'm going to tell y'all right now, and this will help almost every single one of y'all, step up and step down have to have this lower value of 0. So what we do is, although it starts at 20, let's choose this to be 0. And it will go up 20 decibels per decade, then go here and finish out. Now the other one, remember, we have to add them. So it must be at 20. And then once it hits the pole here, it must be 0. So these are the 2 inputs we're going to be using. So we'll say what input 1 plus our second input is equal to our output. And we can label this as 1 and 2. But now what we have to do is we have to figure out what op-amp configuration corresponds to our first Bode plot mapping. So we have a step-up function, which is our number 2. Okay, well, let's draw out number 2. Number 2 here is, it looks like this. I hope y'all can see where I'm getting this from. This is VO, and VN is actually the non-inverting input, which makes it very easy for us whenever they say input resistance. And now we have to add, what is this? Well, the second one looks like, it looks like this. It's a low pass. Low pass is number 3. So number 3 here is this one here. This one's an inverting input here, so this one changes, of course. So we have a non-inverting amplifier and we have an inverting amplifier. All right, so now let's label our values. We can say this is C1, this is R1 and R2. And then the other one, let's say this is R3, I'll do it in blue here, R3, C4, and R4. All right, so step up and step down. How are we going to find R1 and R2? Well, we have to notice that we can use our end behaviors for the resistance values, just like we've done before. So what I want to do that might make it a little easier is we want the capacitor to be shorted so that we can get a non-inverting amplifier configuration. I'll draw it just once here. So when omega approaches infinity, C1 is what it's shorted. I'll draw out our new amplifier configuration. So it's shorted, so I'll draw the terminals of the capacitor. And now the resistances. This is Vn. What do we notice about this? I mean, that's just this. That's just this here. So our non-inverting amplifier, when omega approaches infinity, must be the gain of a non-inverting amplifier, a basic non-inverting amplifier. So, knowing that, what we have is H of omega is equal to non-inverting amplifier 1 plus R2 over R1. When omega approaches infinity, what is the value in decibels of input 1? Well, let's look here. What is it? Let's go trace it back. That's 20. So 20, or our magnitude is equal to 20 decibels, is equal to 20 log of H of omega. This is not the same thing. This is what this should be here, 1 plus R2 over R1. So what creates 20 decibels, just like above, is equal to, well, I mean, what is that equal to? That makes this H of omega equal to 10. So 1 plus R2 over R1 has to be equal to 10. R2 over R1 must be equal to 9. R2 is equal to 9 R1. Let's just choose R1 equals to, I don't know, 10 k ohms. So R2 is equal to 90 k ohms. This is by choice. You can pick it to be 1 and 9. You can pick it to, I don't know, like 9 k ohms and 81 k ohms. It's up to you. It doesn't matter. You choose what we want here. So we have our two resistance values. Now, we have to figure out what? I mean, there's a capacitor in here. How do we find the capacitors? We look at the pole, or zero, that is being affected in our first Bode plot. Now, how do we pick the zero or pole? Well, let's look at the transfer function here of 2. Which one looks easier to solve? I don't know about you, but that pole looks much easier to solve than that 0. It's going to be the same thing, but I mean, it's up to y'all. So let's use the pole, 1 over R1 C1. So pole 1 is equal to 1 over R1 C1. So pole 1 is at 1,000 radians per second. So C1 is equal to 1 over P1 times R1. And this is equal to 1,000. We chose R1 to be 10K. So C1 is equal to, let's check, 1 over 1,000 times 10,000. We get 1 times 10 to the negative 7 farads, or 100 nanofarads, I believe. Yeah. C1 is equal to 100 nanofarads. All right. So we've gotten our values R1, R2, and C1 for the first input, our first op amp. Now let's do this second value, or this second, op amp. So we want to find the resistance values. We look at when omega approaches infinity or 0. We want to choose 0. Why is that? Well, omega is approaching infinity. Our decibel gains will change. Our decibel values will change with time. When we choose omega approaching 0, the decibel value will always be 20. So we know this will always be 20 decibels. Now let's look at our transfer function here. When omega approaches 0 in our circuit, the C4 value, the capacitor, will open, and we're left with an inverting amplifier. Our H of omega for our inverting amplifier is negative R4 over R3. And we know 20 log of the absolute value of negative R4 over R3 is equal to 20 decibels. This must mean log of this is equal to 1. That means R4 over R3 is equal to 10. R4 is equal to R3 times 10. Let's just choose R3 to be 10K, R4 to be 100K. Pick whatever you want, it doesn't matter. As long as it's not too small, not too big, I keep it in the K ohm range. If you want to use 1K ohm and 10K ohms, that works. 100K ohm and 100, that's probably not, that's too much. It's 1 mega ohm, right? Something like that. Keep it to 10 and 100 or 1 and 10. Up to you. So we choose this. Now we need to figure out the value of our capacitor. Capacitor value. We look at our pole that is being that is affecting our second schematic, or second, Bode plot, which is P2. Okay, well, what is that equal to? Well, let's look at what our low-pass filter shows us. This is our low-pass filter. This is our transfer function. Our pole for our transfer function for a low-pass filter is P2 is equal to 1 over R4C4. That means C4 is equal to 1 over P2 times R4. What is pole 2? Pole 2 is 100K. Times R4 is 100K also. So C4 is, let's check, 1 over 100,000 squared. 1 times 10 to the negative 10 farads is equal to 0.1 nanofarads. That's pretty small. So we have our values. There we go. And the reason they're so small, of course, we have to remember we chose R4 to be pretty big. If you want to go back, if you have enough time, and make this more realistic, of course, 0.1 nanofarads is realistic. I mean, you get in the picofarad range. That would maybe be troublesome if you worry about time constants all that much, but I mean, you should be fine. So now we need to put these values to, work here. One thing we have to notice, it says indicate which order the stages should be placed in to ensure that the input resistance does not vary with frequency. What that means is if we have an input we have to make sure it does not vary with frequency. So if we change the frequency, it does not change the value, you know? Input frequency, or input resistance. Remember, input resistance is Vin over In. One thing I like to do is if it ever asks for input resistance to be not varying, choose the non-inverting amplifier. Why is that? Well, remember the non-inverting amplifier has no, you know, that's Vin, this is ground. What is the current through Vin? That's In, but that's always 0. Never change. It will never change. You only have negative feedback in this class. Just choose the one that has the positive terminal. This will always be infinity, by the way, if non-inverting. So you'll never have this change on you. You'll be perfectly fine. That's my kind of trick for y'all to notice this. All right, so I mean, that's pretty much it. You would just put the red first. I don't really want to have to do this, but I'll do that there, and then this one gets plugged in here. This is a resistance. Then just make this quick. This is not the best, but it doesn't matter, right? Okay, and we're done here, and we can put in our value. So R1 or C1 is 100 nanofarads. Or you know what? Actually, I'm going to make this a little bigger so y'all can see this maybe. Okay. Oh man, I love hearing Christmas music already. It's crazy. R1 is, we'll say 10K. R2 is 90K. And now our second, we have R3 is 10K. R4 is 100K. And this one is 0.1 nanofarads. And we're done. If Vin changes, we notice there's no change in input resistance because In will always be 0. Perfect. That's all we need. There we go. All right. I hope this made sense with y'all, or for y'all. I'll go over how the step-by-step, the way I do it. But let's go through that, I guess, now. So the first thing to do when we're doing these, we'll give you this kind of recipe. So we'll do like a recipe for you know, plot to op amp. The first thing I want to do is find poles and zeros. It might make it easier. This might ease you into this type of problem because going face first and just trying to graph everything might be kind of hard for us. So we plot our poles and zeros. Now you make your respective inputs. Make your input 1, input 2, and so on. What I mean by that is we make our input graphs. So whatever our output graph is can be broken down into 2 or more input graphs. Similar to the Fourier transform, however you want to think about this, our output graph can be broken up into more than 1 or 2 input graphs, which is exactly what we're doing. We're creating these input graphs to make them make them similar to the graphs that we've created on our cheat sheet. So 3, after we've made our, you know, input 1, input 2, match the input graphs to the crib sheet. After we're done matching them, draw your op amp. That is this part. This is what we do next. We create our op amp. op amps, and we put a little addition so that we know, of course, we're adding these. Okay, what's next? 5. We look at end behaviors of input to calculate resistances. Remember, this is only for resistances. This is not for capacitances. The next step is for capacitances. For step 5, what we're doing here is we are trying to find we're looking at the end behaviors and we're trying to find the resistance values, because the end behaviors get rid of our capacitances. Our capacitors either open or short. That's what we're trying to do. We're trying to choose our resistance values so that we can find the capacitors. Now, at step 6, we use poles/zeros to calculate capacitors. Or inductors, if you're in Dr. Dave's. I know he gives inductors. In our case, we're only using capacitors, so for us it doesn't matter. For step 7, after we use our poles to find our capacitors, which is this step here. We use our poles to find our capacitors. After that step, after that, you have your capacitor value, you're done. Draw final op amp. Of course, you should go back to step 5 after you're done with step 6 for the second or even third input, depending on how many input graphs you have. But I mean, that's all the steps. This is the recipe to solving these. If you follow this every single time, you'll get it right. I'll write a very important note. When using step up and step down op amps, the lower limit, or the lower line, of course, when you step up, the one on the left, when omega approaches 0, that decibel value must be 0. Must be 0 decibels. Same thing with 4. Whenever you have that step down, that lower value, that lower magnitude must be 0. All right. That's pretty much all. I mean, I hope y'all understood and y'all could, get this kind of work done quickly. If you follow these steps, you'll get it done in 10 minutes. Just do enough practice, you'll catch these kinds of, these kinds of things. It becomes like secondhand. But hopefully y'all understood this. Hopefully my mic isn't dead. Hope not. Let me check. Oh, we're good. Okay. Well, I'll see y'all later. Thanks for staying, I guess.